traveling around and visiting all the institutes and meeting a lot of you people. So I hope I will not deceive you what I'm going to talk to you, because I'm going to talk to you about a life story here. It was mentioned that I'm working for the information, communication, and energy. And from materials perspective, actually, I got my degree in the University of Strasbourg. It was a very fundamental science what I did. But when I arrived in IBM, I learned that you have to take an industrial problem eventually to make beautiful science with it and solve problems in industry. So, having said that, when I was called to go to the Netherlands, I said to myself, what I can do more than I did before. So, silicon is the base material for the electronics today. I was thinking to make a polymer that behaves like silicon but can be processed like a polymer. Okay? Starting synthesizing polysilanes, silicon atoms, hooking up with carbon atoms, and so on and so forth. Here is how my last story started. But today, we have to look also how the technologies are. And here I have a graph that shows that you have mature technologies in the electronics industry, and you have emerging technologies also. Mature or emerging from the market point of view, or from the technology point of view. So you see what one faces when he works in this edge that has to look backwards and see, hey, can I make the link from the two? Can I push through the technology to go further this edge here, or can I push it from the market point of view to push it? But all of this requires a lot of science and technology in material science. So I have chosen today to show you this belief, 3 subjects that correspond, that have to do with my lifetime, starting with IBM. The one is how you can do a bottom-up nano fabrication to make the feature chips, the feature technology of the fabrication. How you can increase the storage in 1 square inch, how you can put 1 terabit. And this is the field that actually I was working in Almaden, the storage devices. Also in the lithography part, how you can make the top-down manufacturing. And last but not least, how you can make flexible devices from this dream that I had to make new organic materials or organic inorganic materials. And I have chosen one subject, the organic photovoltaics, to illustrate all of this. Having said that, now I have to take step by step to walk you through all of this. And the first one is how you can make the top-down nanofabrication is the optical lithography that is used. What you have here, you have the wafer where you put a polymer that is photosensitive, and you have the mask that you can project this F down, or you project the circuitry. You have the lamp that can put the photons to photo cross-link or dissociate the polymer, and you have some lenses here to direct all of this in. So what is the basic criteria that follows all of this column here is the relay criteria. And these features that you will put down here depend on the wavelength of light that you will use, the numerical aperture of the lenses, and a factor K that will depend on the materials and on the various aspects of the geometrical and construction aspects of the column, but also on the materials. So this is a very simple story. Nowadays, what people do, they use also a liquid here that has a refractive index that is bigger than the air to reduce the features. Reduce the features, well, this diagram shows you where we are approximately today in the manufacturing. Intel and all the fabs, they are working with lines of 32 nanometers. I saw this diagram because this is about where I was hired by IBM. You see that at that time, we were much above the diffraction limit of the optics of what we were doing. And I left IBM in '89 that was just above. And at that time, the chemist and one Canadian scholar at that time, Jean Fréchet, was in the laboratories where they invented the chemical amplified photoresist. because I don't have time to explain you how this works. It's a polymer that is sensitive to light and they can decompose or cross-link. In this way, you can fix the features. But you see, the technology was asking to go to smaller and smaller features. You could change the source of light, and so on and so forth. Now the quest is, when you go down, how you can go to this place here to have 10 nanometers. Today, the solution that is provided, and it's a very expensive solution, have cost approximately, the machine that makes cost about $250 million, really, to go to this kind of features for one step of fabrication. So how we can go further? Can we invent something from a polymer science point of view or from self-assembling of molecules point of view to solve this problem differently? Well, I will show you that is possible. And before I show you that is possible, what is done today to arrive to these limits that they are beyond, much beyond the diffraction limit, they use steps. They go 3 times, they pattern the material 3 times, and they use this machine here so that you can arrive to 32 nanometers. So that means that for these 3 steps, you need 3 of these machines that each cost 290,000 euros. Million euros. It was exactly what it cost an airplane, Airbus A380, the latest airplane. So you can see how much is the cost of it. You have also the multi-beamer here that you can go many different times through and make the recording of the features that you want to do. So can we use the multi-beam lithography and the self-assembling of block copolymers? What is a block copolymer? This is what I started when I was a young PhD student in Strasbourg. A block copolymer, there are 2 polymers linked together, and when they are linked together, they don't like each other, so they phase separate, but they cannot get away too much from each other, so they make the so-called macrophase separations. Here you have a phase diagram, and in this phase diagrams we represent the free energy of the system. The chi is the interaction parameter between the red and the blue block. N is the degree of polymerization, which represents the entropy. Entropy makes the Gibbs free energy, and you have the composition. And you see, by playing with these 3 parameters, we can have structures that are lamellar, or cylindrical, or bicontinuous. This we will find them a good use for photovoltaic devices, but the lamellar and the cylindrical, we can find a good use for these nanotechnologies of the bottom-up type of nano fabrication. So ultimately, you see here that these kind of systems that we know how to fabricate, we know how to synthesize, we know their behavior theoretically, so we can go and build molecules exactly the way that we wanted. So we can reach very high resolution because the figures that we can have here depend on the molecular weight. So we can go from 5 to 1,000 nanometers if we want, depending on how big this molecule is. So we have low intrinsic line edge roughness, meaning that the interface between the 2 blocks, it's very sharp because the 2 blocks are separating each other, they don't like each other, so it's very sharp, this interface, and it's a condition that's required for the electronic industry. They can be easily processed, and they are very low cost. Now, are they compatible with the CMOS lithography? Well, we have to control the orientation of domains with respect to the substrate. I will show you how we can do that. We have to control the alignment of this domain so that we can put the features the way that we want them down. We have to have good integration capabilities, because in the process of these lines that the fabs, the foundries for making the chips, need a lot of restrictions. They have a lot of high requirements. We have to have low defectivity, and we have to respect the design rules. So today I will try to show you as much as I can for this compatibility with the CMOS lithography. First, when we started, long time ago, 30 years ago with these polymers, when we put it in a thin film configuration and we spin cast it at 1 temperature, and this is a cylindrical structure that the cylinders are ordered in a 2-dimensional hexagonal lattice. Here you can imagine, eventually you can think, this is the surface, that the cylinders are perpendicular to the board. but eventually when you etch the first layer, you see that the cylinders in the middle of the layer are lying down, and farther on they lie down. So if you use a temperature higher than the T1, then you see that all the cylinders are lying parallel to the substrate. So here with the temperature, we don't have good control. So do we have other ways of controlling the way that the cylinders are lying down of these microphases? The dimensions here can be 10 nanometers, either perpendicular or parallel. Well, we can, and we tried by using a copolymer that we treat the surface. And if we do that, and this copolymer should be a random meaning that the two monomers are randomly distributed on the chain, and in this way we randomize the interaction parameter of the two blocks with the surface they are going to sit, so they don't have any preference of the one over the other. So by doing that, what we have found is that, and when we use the right composition, then we can see that the cylinders are perpendicular all over the thickness. When we make a thick film and then we etch it slowly, we find them that they are going perpendicularly down all. So, but further on, how we can further make them align in one direction altogether. I show you that when you have it in a free surface, then you obtain these pictures that they look like the fingerprints. However, if you put barriers, like I show here, and this has been done, it can be done by the classical lithography. You take a resin, you make small containers here, you fill with the polymer, you anneal it to reveal these microstructures, and then they orient in a particular way, either parallel or perpendicular, depending on the structure. So this phenomenon, we call it graphoepitaxy. This is a Greek word, but you understand the meaning. For the solid state chemists and physicists, they can understand. So here we have, in the nano level, you have a surface that it was patterned with the classical lithography, the 193 resin, and when we put the film of the copolymer inside these edges, then you see that the cylinders are parallel in this case. And we can eventually adjust the surface treatment here in between these ranges here, and then the cylinders can be perpendicular. So here I show you that we can eventually now make this feature that will be approximately 100 nanometers, make nano features inside that each one is 10 nanometers. With the simple process of adding a thin film on it. Well, the point is that once you have made that, and here you see this is the silicon that have to be transferred to this pattern. This is the copolymer that we use to orient the cylinders perpendicular, and this is the silicon oxide, the native oxide layer. So then the process is to remove this block, the blue block, make the holes, and transfer it to the so-called, from a soft mask to a hard mask, which is the silicon, and then change it with a specific plasma and transfer it to the silicon. And that was happened, and here is an example that you have features of approximately 50 nanometers with 70 nanometers depth, and they're well oriented. Now, the next question that remains, how about the defectivity? What you do about the defectivity? You have to make, today in the manufacturing, they are using 30 centimeters wafers, which are big. So if we can put a thin layer of this copolymer, should be zero defect. No defect at all there. So the studies we've done recently, we did a systematic study. Here you see the resins, the Photoresist, and you see the block of polymers, and you have the pitch of this system, and you have the periodicity of the copolymer. And when we adjust and we have really well-defined periodicity of the copolymer and periodicity of the resin, we can see that slowly, and also when we increase the thickness of the resin that goes just on the surface, and we have some theory to explain all of this, that the defects eventually that will be on the ridge inside here on the bottom, slowly they're relieved and they can annealed out by themselves. The rule will be that the L plus S has to be an integer of the square root over 2 of the length. This L is the periodicity of the block copolymer. So if you respect this rule, you see now that here that we call it the Lanois triangulation pattern. Actually, what it does in this what we do in this pattern, we see every spot how many neighbors we have. And since here we have an hexagonal system, the defect-free system, that every spot here should have 6 neighbors. If it has 5 or 7 neighbors, that means that we have a point defect. And as you can see here, we illustrate that we have no defects at all at this level. And you see also by the Fourier transform of this pattern, we have not only the first order diffraction of this structure, but we have higher orders, which means that the single crystal of this material on the surface is enormous. We see some reminiscence also of these spots too that represent the periodicity of this wavy pattern that we put below. But eventually when we put the thickness a little bit higher, then it will disappear completely. And we are capable now to make systems that they are really well ordered in a very big, like here you see 500 lines without any defect. So this is a proof of principle needs to be installed now in the manufacturing lines. In order to do that, and I will not go further on this subject, you have to make polymers that they are free completely from metals, because the manufacturing lines in semiconductor industry don't like to have contaminants and things like that. You have to make polymers that they are more compatible with the process of the etching and so on and so forth. And above all, we have to make polymers that they do not slow down the process, which for this kind of features to appear, so far we need 1 hour of annealing with a solvent of high temperature, but you have to do it in a few seconds. And this is the challenge we are facing now from materials point of view, to go further and make materials that make these patterns just spinning down the film and then relieving the nanostructure that we want. So, well, the proof of principle is that we can, yes, below the 22 nanometers, which is the ITRS, the silicon roadmap, the silicon nanotechnology. So we have, of course, to do a lot of work, and I hope there are many young, bright people around to understand from first principles why these orientations are perpendicular or parallel. So far we did what we thought from the rules that we know in the polymer physical chemistry, but maybe other rules have to emerge in more fundamental ways, so that we don't have to think much more, but we have the rules, the theoretical rules, so that we can design the copolymers in the right way. So I said that we have to remove the impurities. So far we can do it by filtering the materials and removing the impurities, but there are other methods of polymerization that don't use metals. So this is what we're developing now, and we have to use a different composition. For instance, we have at the end the silicon surface. It will be better to make a copolymer that has silicon elements there than the carbon elements, and this is the kind of things that we're working at this moment. Now the second subject, the storage. Here is another lifetime story. Again, I was hired in 1981, and the storage, the density was there, you see. At that time, we were making big disks with iron oxide particles diluted in epoxy resin, and we were coating a surface. Probably some of you remember you had the floppy disks, that they were brown, and they were made out of this technology, so not very high density. But the challenge for us, research time at that time, so we had to make the gigabit per square inch. And before I left IBM, we had a testing device which was 5 times bigger than this table, and we made the proof of principle that we can store in 1 square inch 1 gigabit. And we were working also with engineering part of IBM in Japan, and we were trying to make a disk that was as big as my watch, to develop the motors, to develop the servers and things like that, the servo mechanism that can reach in and read the information. So, and that is where I left IBM. At that time was the optical storage also, and we were saying, well, the competition between optical storage and magnetic storage is very tough. The optical storage will go over the magnetic storage. But an invention happened in France. Somebody who's called Albert Fert, who finally got the Nobel Prize, he developed these magnetoresistive materials. the magnetoresistive materials, and Stuart Parkin, that was working in IBM, in fact, he had hard time from his management, he was trying to put layer by layer metals like copper, cobalt, and so on and so forth to create these magnetoresistive structures. Well, finally, these magnetoresistive materials help to make the reading head of the storage device, because when you have a magnetic field that emerges from these materials, then the resistance of the materials increases. So then you could fly the head that's writing a reading information on disk at relief distances so that you could really make faster and denser storage. So that helped the storage, the magnetic storage to grow up, and you see now we are arriving, well, this is the experimental story, and here we are arriving now some other limits. We are starting getting to a plateau. But what is the solution? Either to work on perpendicular recording meaning that you have the north-south of the magnet between the two edges. This was a technology that we were working at the time, or to use pattern media. The pattern media, what are they? Well, here is the story. Here I have a disk that you have today's technology, where you have the tracks and you have the bits that are written in every track. And you can see that for every bit, you have many microdomains, magnetic microdomains. However, if you go to the pattern media, every single particle that can be 5, 10 nanometers big, provided that it's not super paramagnetic or paramagnetic, you have to have it magnetic, you have to respect the rules of the materials for that. So then you can arrive and have 1 bit per particle. Not only that, just the technology that I show you, that you can make a bottom-up nano-organization, nano-patterning of the materials, so you can have self-made the track. Because I don't know if you remember, when today the disks arrive already formatted. But in the past, we had to format the disk. What you were doing by formatting, actually, you were writing the tracks here. And you are inscribing the information within the track, just to know where you put the information. But now, with this kind of technology that I will show you, that we're trying to do, eventually you have the formatting by itself, by the bottom-up approach nanotechnology. Now, from magnetic point of view, today we are at 600 gigabit per inch, and you see a bit is many grains, many dipoles on the surface. Tomorrow, we would like to have 1 bit per nanoparticle, but in order for this nanoparticle, the magnetization to stay constant, we have to have very big magnetocrystalline anisotropy, which actually, this is the magnetocrystalline anisotropy, this parameter here, the volume of the particle, and this is what I call it the God-given noise, the KT. See, you have the temperature fluctuation, we have the Brownian fluctuation around. It depends on the temperature. If this factor is more than bigger than 50, then you have this thing that it will not switch. Actually, if you have your disk, you don't want in one evening to disappear all the information that is in there. So, and this is what makes it to be stable, this parameter here. So we found out that in the literature, and we have a very good laboratory, ISMCB in Bordeaux, that they have produced these crystals, platinum, iron, and you see here that the different sizes of these crystals, but once you have them, then you have to magnetize them. But when you magnetize them, that you bring them above the Curie point, and then you put a strong magnet on them, then they will agglomerate. So to avoid agglomeration of this, then you put a salt on them, or you put a coating of silicon oxide, so that the magnetic fields are canceled and they don't agglomerate. So we have been capable in this, my colleagues in the ICMCB, to make these crystals, these nanoparticles, which can be these sizes, you see, and we have, at room temperature, very good magnetization, remnant magnetization on the system. So, but what's next? Once you have the particles, then we used the same kind of technology that I just showed you. We used the block copolymers that they can organize in cylindrical structure now, and by modifying the surface of the particle with the hydrophobic tails or hydrophilic tails, we can direct them to go to the one phase or the other phase. Here, this copolymer is polystyrene, polyethylene oxide. This is hydrophobic, this is hydrophilic. And the hydrophilic part is the spheres inside here. So when we put the hydrophobic, we found the particles at the edges of the interfaces between the spheres, okay, and the matrix, which is the polystyrene. However, when we make them hydrophilic, they go inside the microdomains. So this is what we're going to do. And this is what we prove here with the transmission electron micrograph, that we put 20% of particles here, so that not every spot has a magnetic particle, but a few of them. And also we use the magnetic force microscope now to see exactly where they are. So we saw some of them, that they are there. This is the first experiment for a tool that was made by Brucker that allowed us to go and see it, because they made the tool, magnetic force microscope, it can run very fast, very dynamic one. So what we discover here, we see some of them, not all of them, the 20%. But that doesn't mean that they are not there, because if the magnetization is horizontal with respect to the surface, then the AFM will not see it. However, if it's vertical, we'll see it. And that's something that we have to work on. The other thing that we discover here, we discover that we have places, and that has to do with the defects that I showed you in the previous work, that when these hexagonal patterns, they are not well organized and we have defects, sometimes the particles go inside these defects for entropic reasons, because they have a lot of relaxation of these hairs that we have here, so they relax instead of being stretched. Moreover, we measured with this type of nanostructuration of the magnetic particles that the remnant magnetization of these small particles, which at room temperature is approximately 100, and unfortunately the numbers doesn't appear here. Here we have approximately 50 compared to the iron oxide magnetic particle, which is 6. So that you see, with this platinum iron, the magnetocrystalline anisotropy is very big for these small particles. So we have good feature. And further, some new technology that unfortunately I cannot talk much about today, that is under the protection. We have developed a very simple technology where we can put this solution of the block copolymer with the magnetic particles and spin it over a surface, and you see them, they are organized perfectly in a very large surface. And actually tomorrow maybe the disk will be made this way, that we will have this formulation of this sink of block copolymer with the magnetic particles. We will have this new technology of structuring the surface, put the film on it, and structure it by itself immediately. So that will avoid a lot of processing steps. So finally, to say that here on this part, we have demonstrated that we can obtain the small magnetic particles and order them in a very nice way. We're using the direct self-assembling, and we are working now to understand as well theoretically and chemically to make materials that they will be more compatible with the storage industry, so that we can use this kind of technology that is based on formulation of simple polymer science, simple solid-state chemistry of making some nanoparticles. Now, one small thought here is that I was visiting the IQC Institute and the Perimeter Institute, and I understand there is a lot of effort to make the quantum computing. Look, I mean, in this, you can put a single magnetic spin. Around, we can put all these conjugated polymers that I'm going to get into now, in the third theme, that they are also semiconducting, and we have spins there. And the spins in the polymers and organic materials are nothing else but the radicals. So you can have a magnetic spin with a radical to interact and manage it. So nobody has thought yet, but probably we can imagine, and this will be a very good manufacturing possibility to manufacture large surfaces where you can play and have either storage in different dimensions, in several dimensions, because it's the quantum computing. So if you have one spin here and one spin here, they can communicate and so on and so forth. But what the message I'm trying to give you is that there is possibility to make materials that you can control their nanostructuring and in a very affordable and manufacturable way. So the last theme that I hope I can cover in 10 minutes is the flexible organic photovoltaic devices. Obviously, I promised you to talk to you about organic electronics, but what I was telling you in the beginning is that we have to think about what's going on today in the electronics industry and what will happen tomorrow. And I had chosen one subject, the photovoltaic effect. Why? Because the solar energy supply in the Earth is enormous, and the sun is shining in one day the energy that we consume in 1 year in the Earth. So how much we are using that is affordable to use it, and you see here the several spots that is easy to recover. We are using the solar energy, not the photovoltaic, because the solar energy has also the thermal one, has also the thermodynamic one, and so on and so forth. It has the photovoltaic one. It's only 0.6% that we are using. So there is a lot of room of improvement there. So photovoltaic device, and you know, I come from France where the nuclear power was invented, I mean, Marie Curie and Joliot-Curie, and the photovoltaic effect actually was invented by the same family because Becquerel was part of the invention of the nuclear power as well. But he was developing that when Greece just was going out of the Turkish occupation here somehow, for those that they are remembering that. So in the 19th century, that was Becquerel, and it was the same dynasty of Becquerel that was on the Nobel Prize for the nuclear power. But the Becquerel of the nuclear power, what he invented a balance with a piezoelectric crystal, and this piezoelectric crystal balance helped to see the loss of mass for the radium and the uranium. And this is how they invented the nuclear radiation of materials in Paris. So who understood the photovoltaic effect? It was Einstein, and actually he got the Nobel Prize for his photoelectric phenomenon, not for the relativity. Okay? So you see here it took 60 years something, all right? Now, what's next? When was the first invention to make the first photovoltaic device? It was in Bell Laboratories by these 3 fellows, and the power conversion efficiency was 4%. Now you remember, here was the first invention, here was the understanding, here was the first realization of a gadget in the laboratory, and here was the first application in '58 for the satellite, the Vanguard satellite. Now, I put this up and I use it for political reasons, scientific political reasons in France, because, I mean, we have the nuclear power, and if you want to do research in photovoltaic effect, then you say, well, where we put the money? On nuclear energy or on photovoltaics? You see, also it was a French invention, but you know the nuclear power where it is today and how much research was put there and where we are. Well, maybe there is a reason to worry and do something about that, because, so doing about something like that, there are a lot of things that are going on photovoltaic research. And you see, you started here in the United States, well, south from here, the RCA company doesn't exist anymore, but I remember when I came in Massachusetts, they had a laboratory somewhere there outside MIT. They had a lot of work in 3.5s and so on and so forth. There is a lot of energy research in NRL, and also I think in a Boeing company, they can go up to 40%, but this is not affordable really to bring this technology to everybody. But here is where the organic materials, the semiconducting polymers came about to bear. And you see the evolution in a few years. Actually, last week, Konarka, a small startup in Massachusetts, in Lowell, Massachusetts, and they are using the factories of Polaroid in somewhere in in Rhode Island. They announced 9%. It seems like commercially, this plastic, power plastic, they call it, starts to become commercially affordable and probably will come out. So you have the other technologies. This is the dye-sensitized technology from Grätzel from EPFL, and you have, of course, I mean, the thin film technology, the cadmium telluride, and so on and so forth. You have the amorphous silicon somewhere here. No, sorry, this is not the amorphous silicon. It's not even here. The amorphous silicon is approximately 6%. It gets to the plateau. You have the normal silicon technology that is commercially now is 15%, in the laboratory is 20%. So we have room. Why we have room and why this can be important, okay? Well, first of all, we have very inexpensive semiconducting materials, are the polymers or the small organic molecules that they have semiconducting properties. One very important point that I understood it when I was undergraduate in Greece, that these molecules, that they are like the carotenes, where you have alternated simple and double bonds, the strength of the absorption of light is enormous, which means that you can have a thin film and you have more energy absorbed than you have a thick film of silicon, you see? So that's an advantage, often we forgot. You have good flexibility, and eventually we can produce it with roll-to-roll. What are the points of attention we have to give for this kind of materials today? Well, we have very low efficiency, and for that is because we use polymers that they absorb only part of the solar spectrum. We have to make them to absorb in a large part of the solar spectrum, and this is what we call in the low band gap. That means the energy gap is from towards the infrared, where the light is more strong. So we have to have better improved stability. Well, we are stable for 70, 80 years now, but we are shined by light. We have molecules that they are dismantled, they are cut down, but we are auto-repairable at the same time. So this is some challenge for the young chemist, where we have these molecules, can we make them auto-repairable? And if we cannot, can we encapsulate to avoid the intruders like water, like oxygen and other things? And this is the way it's going now. We have to find encapsulated materials. Last, and this is what I will show you an example to convince you that we can go towards the commercialization. You have to scale up the manufacturing and use technologies that they don't need to high temperatures and slow down the manufacturing process. So you have to formulate stable inks. So I will make you here on the board a device of this photovoltaic device and show you the process, how it happens when a photon is absorbed, because they differ a little bit from what is in inorganic materials. Here you have a substrate, which can be a PET, we call it, the indium tin oxide, the transparent electrode. We put a conjugated polymer, it's a polythiophene complexed with a polysulfonated styrene. Essentially, we put it to remove the roughness and also to protect the indium tin oxide that the indium moves and goes up to the device. And we use a blend of a material. And then on top of it, we put, well, these are the thicknesses just to compare things. It's 100 nanometers, sufficient for this kind of device to absorb enough light, since I told you that the strength of absorption is much larger than in organic crystals, and you have also an aluminum. So the ingredients is a polythiophene, C60, the carbon, the blue material, and we have then a photon is absorbed, and we form the so-called exciton. Actually, when a photon energy is absorbed, two charges are created, but they are linked together by a string that is below the polymer chain. So they are not separated. And this is the basic difference with the inorganic semiconductors. When you put a photon in, you cut the bond, the silicon-silicon bond. Here you cut only the bond that is p electrons, not the sigma electrons. And then they start moving around. They are moving around and they dissociate it and they go, you see the negative charges, they arrive to the electrode. And this one guy tries to go out, but cannot come, it's killed, because it's a cul-de-sac here. And the other guy came, so now you have electricity that comes out. So you saw the challenge. You have to make a polymer material that has bicontinuity and not cul-de-sac. You have to make these distances to be around comparable to the lifetime of these excitons, which is about 10 nanometers. How you do that? Well, you have to do certain other things. You have to adjust also the energies of these materials that you'll do. So that means the conjugation length. So when a photon comes in, they can move it from the ground state to the excited state. And then you have to have the next polymer, this we call it donor, this we call it acceptor, that they separate the charges. So, and then we have to remove it. We have to adjust the interfaces here and the levels of the energies and so on and so forth. And all of these have to be a good design of materials. Of course, I can give you 40 hours lectures that I give in my school there to explain to the students. And actually, you'll be happy, and I'm happy to announce you by the end of this year will be a textbook on this field, not on the photovoltaic, but the organic electronics. So, and then you have to control the morphology, as I just showed you, by using, again, to make it stable, the material, and also to dissociate the exciton's. Here again we go. Here we have block polymers, but this time different ones a little bit. This one is rigid, and this is flexible, simply because we put this conjugation, the simple double bonds, and the molecule becomes stiff. So you have rods. And since you have rods, then the rods interact also in this way, or in this way. So we have to take into account this kind of interactions. And here we make various polymers to establish the phase diagrams. When the interactions are weak here, then we have this phase diagram where we have isotropic mixture, we have a smectic transition here, and then we go to the nematic. In this one, when we have more interactions between the two polymers, then we can have all the type of features, the spheres, the cylinders, the lamellae, but they have two different lamellae here, since we can play with the interaction of the rods, and this is a line, theoretical line that predicts us that. You can have the rods to align well in the sublayer or be disaligned. But that will be important for the transport of the charges, the electrical charges. If here you can go by hopping very easily, but here, if the mean free path of the hopping of the charge is less than the randomness of this kind of disorder of the cylinders there, then you will not have good transport. You see now we have a good tool to play with the chemistry and make right materials. So what I will show you, just to reach the end of the talk, we made a block of polymer of polythiophene, poly-4-vinyl pyridine, and we use the poly-4-vinyl pyridine here, which has 2 electrons that can complex and have weak supramolecular interactions with the C60, so that we can make the donor phase and the acceptor phase by freeing up and having the organization of that. So we'll use this copolymer with a blend of polythiophene PCBM that is used for those that you are working on a photovoltaic device. This kind of blend is a typical one that is used now in academia, but also in industry. Konarka is using some of this for the first modules they have made. So how we can use it so that this phase separation you saw on the device that I built on this board can be such that we optimize the morphology. So we use the device that we call it inverted for those that are introduced to the system. The normal device will be the indium tin oxide and the active layer. So that means the anode, and this will be the cathode. But in this device, we put, instead of putting P.PSS here, we put titanium oxide. So we transform the anode to a cathode, and we use molybdenum oxide silver to have here the anode. And we used this mixture, the formulation of these 3 materials, 2 polymers, a block of polymer and a homopolymer, and a particle, acting as the donor acceptor, and a block of polymer acting as an additive that will nanostructure again this polymer blend, and also reduce the interfacial tension between the homopolymer phase and the nanoparticle. So when you do that then, we like to study the device performance and the active layer morphology and see how we perform on that. So here I'm showing you directly the results of the power conversion efficiency of the pure blend of P3ST C60. And when we add this block of polymer, we find that at 40%, without annealing, just by spin casting the mixture down, we obtain better than performance than the homopolymer, the neat blend, when we anneal it for 24 hours. So that tells you that something from manufacturing point of view. So that means that we put an additive in there, and we make, this additive works like you use the mayonnaise of oil and water, actually. I mean, you have taken sometimes water and oil, you shake it, and when you leave it, they phase separate again, they become oil and water. Okay? Here, by putting in this system, if you put a little bit of soap, then you shake it and remains, and you make a mayonnaise of oil and water. So we did the same exactly. We used the same principle here. What we did is we used this block of polymer that I show you, and this block of polymer does other things, improves the morphology, and I will show you in a minute with other type of measurements why that. Furthermore, here is the addition and the progression of the power conversion efficiency when we add the copolymer as cast without annealing. And when we anneal it, we see that for the 80%, we go even one performance. Without annealing is 1%, the performance of the pure blend. And with annealing, we go above to, it's about approximately 4.5%. We increase 200% improvement. You see it by yourself that, okay, but the point that I would like to make here is that kind of technology that we are developing, which can be universal actually. This is an example that I show you, polythiophenol C60, but can be any of these other polymers. Now they show very high performance. By making this additive, or additives of this sort, engineering the surfactant, I would say, you can make better performance of devices. Now, why is that? So we did what we call it grazing index X-ray diffraction. We have the X-rays coming out, and we see the spectrum, and we try to analyze the structure of this thin film. So you see here the total, when we take the radial integration of all the intensity around, we see that we have, before annealing, as cast, high crystallinity of P3ST, and then it reduces a little bit when we add the block of polymer, and also the aggregation of the PCBM. This is the fingerprint of the PCBM. It reduces a bit when we add the polymer. So the crystallinity reduces a bit, but that's not a great problem, but it's actually good. And then by comparing these two diagrams here, this is by integrating the intensity on the plane here, the XY axis, in this direction. And we compare this to the integration of the intensity in this direction. What you see here, you see that on plane we have higher intensity for the one that we added the block of polymer, and here out of plane we see reducing. So what happens really here is that when the polythiophenol is crystallizing, you have these rods that they are also like planes. They are crystallizing parallel to each other. Now, when you put this block of polymer, instead of the crystals to go down with respect to the electrode face on, we say, they go, edge on. This is apparently what happens as you cast it, the pure blend. When you put the copolymer, they go face on. And you can understand when it's face on, then the charges that you will create on this conjugate material, they will come out from the electrode much easier than when they are edge on. And you see, this is what we find out, that we increase the phase on configuration with respect to the edge on configuration. All right? This is what you want to do, and you can engineer it. But this is not the end of it. So we did also neutron reflectivity to try to see what is the composition distribution of these two elements that we have there, the polythiophenol and the C60 on the system. And these are the neutron reflectivity of the pure blend and the blend with the block of polymer. And what we see here, we see that also before annealing and after annealing, we see that here you have the interface of titanium oxide, and you have the distribution of the C60 in the system, and you have on the surface of the device, or otherwise saying the anode of the device. So we see that at this place we have a rich P3ST phase, and here we have the C60. And the C60 arrives in the interface and stays there. So we have a layer that electrically is negative close to the cathode. That means that we will pull the electrons much easier. So, and here I have a better picture that compare the real space where you have the titanium oxide, and this place, you see it here, this layer. So you have a segregation, if you want, of the C60 close to the cathode, which helps the dissociation or the transport, the exodus of the negative charges. And from this side, you have and an enrichment of P3HT that helps the holes to come out. And this is never shown before. It's the first time that we unveil how big the role of this interface can be. For the moment, we do not have control. We have just understanding what's going on, and I hope in the future we'll do more work towards that direction. Just this, what I explained you, was a small example to show you that by using these additives, we can increase the power conversion efficiency without annealing, and also we can increase the exciton dissociation and the transport because we make a better interconnectivity on the system, and also we can increase the orientation of the crystals with respect to the electrodes. Finally, what I want to say, once more, the block copolymers for formulating photovoltaic devices, it's a way to go in order to improve also the formulation of these materials and also the manufacturing. So that is my life story in the sense that the block copolymers was the things that I did in my PhD studies. The technologies is what I learned in IBM, and I try with you, I hope, in the future to go further. And this is the group that I set up in Bordeaux area. Well, I mean, there are many PhD students, they are working on these fields, and colleagues that they help me when I are not around. This is the Arkema, which was a division of Total, okay? The National Science Foundation of France, ANR, Agence Nationale de la Recherche, the County of Aquitaine, and the Chair of Excellence. Bordeaux is a beautiful city. It's not only known for its good wine, it's known also for its good science. I hope you are welcome to come and work with us and push forward these fields. Thank you for your attention.
So, I'm sure that President Hadziioannou will try to answer questions at the round. Yes.
Yes, please.
A question. You were talking earlier about hard drives using the nanotechnology, making the domains smaller, using that technique you have there to get really, really small domains on the surface of a hard drive flatter. Just wondering, the idea I see or the concern I have, and can you maybe comment on this? I mean, if you're...
I know where we're going. Okay, go ahead.
The particles so small, your domains so tiny, how are you going to access those? You've still got the camera, the lenses have to move, they've got bearings. The hard drive itself spins, it's got bearings with looseness, plus the whole hard drive vibrates. I mean, I can't find a hard drive anywhere in a store that doesn't vibrate palpably. So
well, I mean, when I was working at IBM, I couldn't think that we can use these pyrophoric particles, we call them. You know what is pyrophoric?
Catch fire, easily?
They catch fire, yeah. Pyra in Greek is fire, okay? Phoric, yeah. So I couldn't imagine, now we can make them. I don't know if you're aware of a project in Europe that's called Millipede. Okay, the slider that was fabricated that had multi-thousand tips. Okay, the technology is there. It's manufacturable, I don't know. Everything is manufacturable if you want to. It's a question of cost. Thank you for the comment. This is a challenge. I'm trying to find a company. I hope these companies in California, where I was in San Jose, they will allow us to try to test these things. I'm sure they are working on that because it's not for nothing Hitachi and others, they are interested in that. It's a challenge for the future, okay? So I think it will not, if we stick to the point of using a mechanical read and write, yes, we have an enormous, not technological, I would say, industrialization challenge. But it's not for nothing that in the meantime I mentioned to you that the quantum thinking with the spins, we can go optically eventually to see it. Okay? And this is, I'm leaving it open to you to think, because you can have a beam that goes, and if the beam is influenced for the spins coming up and down, then you can read it. Why not? Okay? Then you are not limited, neither on speed nor on contact. But I'm limited in my lifetime and my knowledge on these things. You are young people around, think about it. I'm not preaching like a Greek priest, you know. I'm preaching and saying that this is real. This will happen. Well, again, there are two solutions. One is there, but industrially may be difficult. The other is just fundamental, just to prove it.
Well, George, my question is very sort of naive type of question. If you take the silicon crystal, and suppose we consider, say, 1 meter square silicon crystal, and then you use a lot of oil, a lot of energy to produce that, a lot of sand from the sea and seashore and everything. So if you take that square meter of silicon crystal, and you take 1 square meter of your polymer, what is the relative cost between the two?
10,000 times.
So the polymer is cheaper by,
yes.
by 10 to the 4.
Yeah.
So that's
we made, no, it's not only that. I will say you that, unfortunately, I don't have this slide. I gave once on the French embassy in Japan. I gave a talk for the administrators there. The CO2 that you produce is enormous also, because you consume a lot of energy to make the silicon 1 meter square. So this is another challenge. Eh? Right. So, and we have now technologies to catch the CO2 and make the polymers. So not only you don't produce CO2, but you reduce it to CO2.
So what is the raw material of producing these? What is the raw?
Chemicals, carbon.
Gas? Is it natural gas or what?
So far, yes, it's fossil materials. Well, yeah, but we are using today, we are trying, we have a program, and actually with Arthur we were talking about even today, we have a program that we are trying to use renewable materials from the pine trees, for instance. We use this material also for making the resina, the terebinthine. So it's from the family of terpenes, and this chemical, we can use it and to make these polymers. See, the resin from the pine tree? Yeah. There are many things that still open, all right? The resin from the pine tree, you can use to make this material. So, as an example, it's simple to say, difficult to make, but then, well, okay. There are a lot of renewable materials out there.
Dr. Sun?
Yes, I think you should be aware of there are recent progress in making organic, inorganic for the photonic devices like
the hybrids.
Yeah.
Yes, of course.
Dark silicon and coating with a very thin layer of polymer, but using the polymer instead of using it as the active layer, using it as a blocking layer for blocking electron in the hole, right?
Yeah.
So the sorting still taking place in the silicon. Then you have higher mobility in silicon than those polymer stuffs. So what's your comment on that? It's going to be...
My comment is the same that I made in the beginning. The way to come into that, we have to go through the hybrid technologies, to marry them in the beginning so that lower the cost, because we just said the silicon is very expensive, use a bit of polymer, bring it to the market, use the clients to use it, and then slowly feed them up with only polymer. But you brought many problems here. You brought the problem of mobility. Well, I don't have a lecture here to give you again. The mobility on polymers, it will be...
Less than 1, right?
No, it can be ballistic. Because for me, the graphene is a polymer. And the graphene has the same structure as these polymers I show you. All right? The nanotubes is a polymer for me. It's actually a chicken wire, and it's made from the same carbon that we are making these polymers. It's the sp2 hybridization carbon. And it's the same carbon that you have in carbon nanotubes and the graphenes. And as I was explaining to my daughter, look, you have a chicken wire, you bend it, you make a nanotube, all right? And these graphenes, you know, well, I mean, you will Scotch tape, you can get a Nobel Prize, but you have it. So the mobility is there. The problem is that we have the so-called ionization potential and electron affinity. And this electron affinity for some of these polymers and materials, including graphene, is very close to the air, and so they can be oxidized and so on and so forth. So that means the energy levels can be filled. So we have energy levels that they are filled, and we don't have valleys they can go through, okay? it's like this range here. If I jump in myself, I can run. I can't go here, I cannot run because they are sitting, these guys here. This is exactly what's happened. This is what I'm telling to my students. You have levels of energy and you have charge transport, carriers. Okay? And the unfortunate thing for some of these materials is that these energy levels, they are filled up. And this is why we have to find ways to prevent that filling up so that we have enough alleys to go through. Anyway, the hybrid materials will be important. I think we're discussing around for the plasmonics. Yes, sorry.
One question is, what's the lifetime stability of this polymer solar cell? Silicon solar cell claim for 10 or 20 years, so how about the organic solar cell?
Well, it's the same kind of question previously. If you encapsulate, it can be forever. You have to prevent them, the water and oxygen comes in there. Okay? So. And.
So still depends on something. But I heard people say when they run in the lab, they run the solar cell, some device, even the device you test it, it's working now, and after a few days, you retest again, it looks die.
No, it can die immediately also. Okay? If you put a jet with oxygen there, it will die. Sorry, I mean, let's, if you take what I said, the three challenges that we have to increase the efficiency, we have to encapsulate them all to have them auto-repairable, because these materials work, the doping of these materials happens with oxy-reduction. We remove or add electrons, okay? So it's a chemical process. Okay? It's not exactly the same thing that happens in the classical silicon. In the silicon, you cut the bonds, but because solids staying there, the electron levels are deeper in, so you don't oxidize them so easily. So the only way to go is to make them stable against oxygen and water, and also encapsulate them, and then they will live forever. Now, are there technologies to do that? On top of it, the encapsulation has to be transparent. If we ever want to make a paint and paint our buildings, well, there are people working on this thing. Well, we all want to work on photovoltaics, and what sometimes when I see the literature, I become a bit worried that everybody jumps to see the active layer only and not what goes around. And what goes around is more important than what is the active layer, I think, today. So, if some of you want to work on encapsulating materials, you are welcome.
But the problem, George, is that that subject is not sexy, it's not, they cannot get money, they cannot get research money.
I know.
The same thing with packaging of MEMS.
Yeah.
And MEMS is quite advanced, but packaging is well behind it.
Yeah, I mean, here we go. In IBM, when I was working, starting, we were making the cooling element of the microprocessor, which was a ceramic. That was a dirty business because you have to make a polymer, fire it up, make a good ceramic. Nobody wanted to work on that because it was not as sexy as you said, but it was a need.
Right.
So yeah, at some point we have to make. Well.
Any other questions?
Sorry, about the nano lithography using the polymer. Because we now combine with e-beam writer with and narrow imprint technology, you can basically put those nanostructures small as 20 nanometer on any type of substrate. But for the polymer, I think you have to consider what type of template you can use, right?
Well,
there's some limitation.
Well, next year I will come here for other reasons because we have cooperations. I will tell you about the new technology that we developed that I couldn't speak. You don't need to have imprint, you have to have a soup and makes what you need with a laser beam, and that's it. So it's simple as I say it. And cheap, well, of course you have to put the added value to get some money for the invention, but I mean, it's cheap. It costs 1 penny, the polymer, so.
Okay, and I think we'll close since it's 5:45, so please join me in thanking Dr. Hadziioannou for